Okay, here in 2.2, continuing our talks about inference. And this one, we're going to talk about what makes something statistically significant and what is a p-value. So a lot of times we see things happen in the world where it appears like something significant is happening, like the ice caps are melting and global warming and we're using too much oil and things like that. But the question is, how much is too much? How much really is abnormal? How much is too less? How far away from what's considered normal is truly abnormal, meaning what is really statistically significant. So for statistical significance, we're going to consider our null hypothesis as our starting point. So the null hypothesis, we're going to learn more about the null hypothesis in the next section. It's usually denoted with an H sub naught. Naught is null, or our starting point, and H, of course, is for hypothesis. So the null hypothesis is actually a statement about the assumed sampling distribution of the statistic. And this is our starting point. So general in null hypothesis, we are assuming that there is really no change from the status quo, from the norm. So they had lots of examples in the videos. So but one thing I could say is maybe in December this year, it seemed warmer than usual, right? And maybe the average temperature in December in Alaska this year was like 35 degrees. It was pretty warm. So that seems higher than normal, right? But is it statistically significant? Well, the null hypothesis would be that there really is no difference. It's not that much higher. So we would go to our records and see what is the average temperature in Alaska in December. Whatever that average is, usually every single year, that would be our null hypothesis. And then we would try to prove then that our 35-degree December this year is higher than normal, higher than that normal null hypothesis, okay? So to do that, we're going to calculate a probability called the p-value. So the p-value is a probability calculated based on a sampling distribution. That we assumed in our model. So in the temperature example I was kind of just talking about, I would look at what is the probability of the temperature in December in Alaska being 35 degrees or even warmer than that. What's the probability of it being that warm? If the probability is high, then I would say it's really not that significant for the probability to be that high this year. If the probability is really low, then we're going to say, wow, the chances of this happening, the chances of us being all of a sudden super warm here is not very probable, and something statistically significant is happening, okay? Basically what we're trying to do is we're trying to rule out chance. So chance is the random chance that something might happen that's not normal, but really isn't that abnormal, okay? It's kind of like guessing on a test. If you guess on a test, by chance, you're going to get some of the answers right. So how many answers would you get right on a test where it takes to the point where I might think you're cheating? Because obviously you shouldn't be able to guess all the answers right. but maybe some of them. So how many answers could you guess right? Or could you say you guessed right before I start thinking that you cheated? That's p-value. That's statistical significance. So in this first example here that they talked about in the video, we have this basketball team, and there's 5 girls in this opponent's basketball team happen to be really tall. Their average height is 66 inches, and the population average height is 64.5 inches. So is it statistically significant? Is this basketball team way taller than the average? Is this team being stacked against us, basically? So to do that, we're going to calculate the probability of these young women having an average height of 66 inches or more based on this population. So the first thing I need to decide is, okay, what type of population do I have here? Obviously, we like to do normal populations, but there's only a few ways that we can do that. And in order to talk about this being a normal probability, it needs to say that it's normal. I need to have a sample size of more than 30, or I need to have a population that is normally distributed. In this case, it doesn't say it right here, but I think it says it in the video that the population is normally distributed. Okay, if you think about the distribution of heights among any population, you're always going to have like an average height up here, and there's always going to be a couple really tall people and a couple really short people. So it ends up being normally distributed. Okay, so I would like to see that in this actual problem here, but since it's not, I'll just write it anyways as if they didn't leave that out. We'll say the sampling distribution is normally distributed because you have to give a reason before we just start doing things with normal distributions. Otherwise, they're going to say you left things out. So it's because the population was normal. Okay, so the central limit theorem allows us to say a sampling distribution is normally distributed when the population is normal. Okay, so that's the reason we're going to use here. So now that I've clarified that we're looking at a normal distribution here, I can use all of my tools that I have for normal distributions to find probabilities. And again, we're looking for the probability that a average height, so I'll say X bar, is greater than or equal to 66. Okay, so there's a few ways that we can do this, and I don't even need to put the bar, I think. We'll just let it be X. So let's talk about, we can do this with or without a calculator. If I'm not going to use a calculator, then I'm going to want to use my standard normal table. We always use our standard normal table to find probabilities or areas or percentiles or z-scores when we don't have a calculator. If we do have a calculator, then we can use things like inverse norm and normal CDF and normal PDF, okay? So let's start with no calculator. We have no calculator here. So I'm going to try to use my standard normal table. My standard normal table, though, only gives me the probability that a value is under a z-score. So the first thing I need to do is I need to change this x value into a z-score. So remember to do that, you take your x value, x value minus the mean divided by the standard deviation. Okay, and since we're in a sampling distribution here, our mean is the mean of the population, but our standard deviation of a sampling distribution is going to be the standard deviation of the population divided by the square root of the sample size. So we always have to make sure we're using the correct mean and the correct standard deviation in these problems. This is a sampling distribution, not the population itself. So when I plug in the numbers we have here, let's see what happens. So our x is 66. The mean of our population, it says, is 64.5. The standard deviation of the population, I don't think I caught it on here. It did say in the video that the standard deviation of the population was 2.5 inches. I don't know why that got cut off. So 2.5 inches divided by the square root of our sample size. There's 5 women on this basketball team, so our sample size is 5. Okay, so when I do that, I get a z-score of 1.34. So the probability that x is greater than or equal to 66 is the same as the probability that z is greater than or equal to 1.34. Okay, so we're getting there. But again, my standard normal table only gives me the probability that z is under a certain value, not over. So I need to change this to z is less than or equal to 1.34, which is going to give me it's going to give me the complement of the probability. So I'm going to do 100% minus this complement to get back to what I need, okay? So 1 minus the probability below will give me the probability that it is above. So now let's go ahead and go to our standard normal table and look up 1.34. So let's see. 1 positive 1.34 right here. 1.34. So that's 0.91. We can round it to 0.91. Is about 0.91. Okay, remember that's just the probability. We still have a 1 minus here because we want the complement of that. So now when I subtract 1 from that, we get 0.09. So the probability of a basketball team of size 5 having an average height of over 66 inches or above is 0.09. So a 9% chance of having a basketball team with an average height of 66 inches. 9% isn't that improbable, but that is what we call our p-value. So our p-value here is 0.09. So 9% chance isn't that unlikely. We're going to put some actual numbers to these to say how what probability do we want to see in these situations in just a minute. Okay, but first let's talk about how can I get that same p-value using my calculator. So going back up to this bad boy here. Okay, when we're using our calculator, I don't have to standardize things. The calculator is able to give me these numbers without being standardized first. So to do this, greater than or equal to 66, on our graphing calculator, we're going to use the normal CDF option. Remember, normal CDF gives me the area or probability under the curve for whatever interval I choose. So we're going to choose the interval 66 or above. So starting at 66 all the way to infinity. Of course, we can't put infinity into our calculator. So I'm going to put like 99 million or something, as many numbers as I want to push in there to make it big. Okay. And the next thing I have to put is the mean, which we said the mean was 64.5. And the standard deviation, which is again, the standard deviation of the population divided by the square root of the sample size. Okay. The standard deviation of a sampling distribution is not the exact same as the standard deviation of the population. So it's not 2.5. Okay, so let's do that. Calculator. Boom. Come on, calculator, turn on. So you go to your distributions menu by hitting second bars, go down to normal CDF. CDF gives me a range of values, right? And we want our lower bound to be 66, our upper bound to be infinity. Can't put that in, so let's go until I get tired of cooking. Mean is 64.5. And standard deviation is, I put the whole thing in here, 2.5 divided by the square root of 5. Could I have found the decimal first and put that in here? Sure, but why? I don't know. Paste. There it is. Enter. There's my answer. It's about the same as what we had here. We had our p-value was 0.09. If I round this to the nearest hundredths place, I get the exact same thing, 0.09. Okay, so that's the probability of randomly getting a basketball team with an average height of 66 inches. So maybe it was random. There's just a 9% chance that this basketball team was random, but So is that statistically significant? Is that p-value small enough that we can say this is not probable? They must have stacked their team on purpose. So the numbers that we usually use are right here. So these are guidelines for statistical significance. So you can see at a p-value of 0.9, we're looking at here. Less than 0.1, but not bigger than 0.1. So we're down here, which means it is tending towards statistical significance. It's going to happen less than 1 time out of 10. Generally, when we're looking at p-values, we want to be either in this range or in this range. We want to be statistically significant or highly statistically significant. Those are the places we want to be. So we're down here at tending towards statistical significance, which means it's really not that far away from the norm that we can say that they for sure stacked this team against us. Okay, so guidelines for statistical significance right here. Some cautions though about these guidelines, some things to be careful of. They go over these in the video, so I'll write them down again here. The first thing is these cutoff p-values of 0.05 and 0.01 are arbitrary. And I am paraphrasing a little bit. Which basically just means that we have to be careful of being super strict about this. If I had a p-value of 0.051, that's really close to 0.05. We wouldn't want to dismiss that kind of a p-value just because it's right there at the cutoff value. You kind of need to think of them in context sometimes. Okay. The second warning was that some results are going to turn out to be statistically significant, even if they aren't practically significant. So some values will turn out statistically significant. Statistically significant when it's not practical. So again, you really have to look at the context of your problem and say, okay, is this really practical? Are we really saying this? I mean, sometimes it can be that there's never going to be a 0% chance of something happening. Okay, if something has happened, then there's at least a tiny percent chance that it happened just randomly. So even though something may seem way far off and totally statistically significant, that doesn't necessarily mean that there's any funny business going on there. Sometimes crazy things happen, and sometimes it really is random. So we have to look at the context of the problem and consider the fact that sometimes things really are just weirdly random. All right, last one, actually, I don't know why there's 4 here. If you repeat a study many times, you'll likely get a statistically significant result some of the time just because of random variation. So if you repeat a study enough, you'll likely get a statistically significant result just because of random variation. So this is just saying you're going to have outliers. You're going to have a random person who's 7 feet tall. It happens. The wider the net you cast, the more samples that you take, the more likely it is that you're going to end up with one of those outliers. And that's all that this is saying. So again, you got to think of your context of your problem. You got to be practical about these things. And when something like that comes up, make sure that you address it. Just kind of, write something down that, this could really be just random. All right, so let's look at something else here. So this was the, it was the Guy Sorton I forget, like marble or something under the shells. So he is kind of like the ball into the cup thing, where you have the ball under one of 3 cups, and you mix them up real fast, and then somebody has to guess where the ball is. It was the same thing, but I think it was like nutshells. So this guy, he plays the game for 24 people, and 14 people are able to guess it correctly. So the question is, if 14 out of 24 people are able to correctly guess the location of this thing that's been mixed up so well, can we say that that seems like a lot? 14 people out of 24 people got this right. So is there just 14 people that are really lucky at guessing? Or is this guy who's mixing up these nutshells not fast enough and good enough at his job to make it hard? Are they able to track where that ball is going, so they're able to not just guess, but actually know where it is? Okay, so that's what we're trying to determine here. Is 14 out of 24 a lot? So in this case, we don't have a normal distribution. Okay, the probability the distribution of people who can guess correctly out of 24, that's not a normal distribution. It's actually a binomial distribution. Okay, and they go through the process of confirming that in the video. Remember, anytime that you think something is a binomial distribution, we have a set of 4 things we have to check before we just say this is a binomial distribution. Okay, you have to check and see if there is, if each trial is independent. If one person gets the correct answer, does that affect the chances of the second person guessing the correct answer? Yes or no? If it doesn't, then we're good. You have to make sure there's only 2 possibilities. Either they're going to succeed or they're going to fail. Yeah, they're either going to guess right or they're going to guess wrong. We have to make sure that the probability never changes. The ball's only going to be under 1 out of 3 cups. That's never going to change. They're not going to add another cup. They're not going to add another ball. So the probability is going to stay consistent. Okay, so yes, it's a binomial distribution. Okay, and so if I was doing this on a free response exam, I would want to make sure I write that out so I confirm completely that this is truly a binomial distribution before I just go with that. So we already have the formula for the probability of a binomial distribution. So we're trying to calculate the probability in a binomial distribution that x is going to be greater than or equal to 14, either 14 or more successes. So starting here, this is the probability that we have exactly 14 successes. And this is, again, in your formula sheet. You know, you have your, let me write it down. It was p to the, I forget what letter they use, but p to the x power times 1 minus p to the n minus x power. I think x might have been r. So we've done this before. So the probability of having a success is 1/3. There's 14 successes. The probability of having a failure is 2/3, the complement of a success. And there was 10 failures out of the 24. So when we calculate all that, you can do that by hand pretty quickly, and you end up with 0.007. 0.007. And they give you a table down here for whatever reason to show you that as well. The probability of having 14 successes out of 24 is 0.0071. The third way we can get that 0.007 is using the binom PDF on your calculator. But again, I don't want to know the probability of just getting 14. I want to know the probability of getting 14 or more, because we're assuming here, maybe, that this game guy is not very good at his job. And so too many people are guessing correctly. So what is the probability of not just 14 getting it right? What's the probability of 14 or more getting it right with this guy, the way he's operating? So to get that, that's a cumulative CDF. So that's what we're doing here. Okay. And rather than doing 14, the probability of 14 and higher, they did the probability of 13 or lower and then subtracted it from 1, which works. It's just a complement, right? So when you get these cumulative binomial probabilities where you have to find the probability of more than one x value within a binomial, we said if you can't do this with normal approximation, then you're going to be allowed to use your calculator. Okay, so this is the directions on how to do this with your calculator. So I grab a calculator and I go to my distributions menu, second bars. Oops, I got to turn on. Second bars, distribution menu, and you go all the way down until you find binom CDF. Where binom PDF will give me the probability of one X value, so like 14. This will give me the probability of multiple X values, a range of X values. So I put it in there. And so the reason why they do this way, so we're looking for the probability actually that X is 14 or higher. So that would be the probability that X is 14 or that it's 15, all the way to all 24 people getting it right. Yeah. But instead they do it this way because like the standard normal table, that doesn't give you an option to choose your range because it's only going to do at or below, okay, not at or above like we want. So to get at or below, we're going to do 1 minus at or below 13, right? This is a discrete distribution. So anything that's not at or above 14 is going to be at or below 13. So, but we're going to do 1 minus binom CDF. Since we can't do an upper boundary, we have to do a lower. So the number of trials is going to be 24. Go back here. Number of trials, there was 24 trials. The probability of a success is 1/3. And the X value that we're starting at is not 14, it's 13, right? Because we want 14 to be included. We're looking at the complement right now. So I paste that, and then we get 0.989. So I do 1 minus that to get the above percentile instead of the below, and we get 0.01. So that was 24, 1/3, 14, and we got, what was the number again? 0.989. That's 1 minus 0.99, which is 0.01. So 0.01, 1% chance of 14 or more people guessing correctly just by chance. So we're going to say this guy needs to step up his game a little bit. Okay, let's do one more example now. Actually, no, we already did this. We did this exact one actually on the last page. So that's it.